Good morning to all. In this video, we solve one problem on design of spur gear. A pair of carefully cut spur gear with 20-degree FDI profile is used to transmit 12 kW at 1200 RPM of pinion. The gear has to rotate 300 RPM. The material used for both pinion and gear is medium carbon steel, whose allowable bending stress may be taken as 230 MPa. Determine moduli and face width of spur pinion and gear. Suggest suitable hardness. Take 24 teeth on pinion. Modulus of elasticity may be taken as 210 GPa. First, write down all the given data. We refer Design Data Handbook by Lingaya, Volume 2. Class of gear is carefully cut spur gear or Class 2 gear. Pressure angle is 20-degree FDI. Power transmitted is 12 kW. Speed of the pinion is 1200 RPM. Speed of the gear is 300 RPM. Allowable static stress for pinion and gear is 230 MPa. The material for gear and pinion is medium carbon steel. Number of teeth on pinion is 24. Young's modulus for gear and pinion is 210 GPa. He asked what is the moduli and what is the face width, and also the surface hardness for pinion and gear. First, we calculate the number of teeth for the gear. We know that velocity ratio equation. From that equation, we find out the velocity ratio, and also from that equation, we find out the number of teeth for the gear. Step 1. Identify the weaker member. The pressure angle is alpha equal to 20-degree FDI. For that one, the Lewis form factor equation is given here. Find Lewis form factor for the pinion and gear. To decide the weaker member among the two, the following table has to be formulated. The value of sigma naught is given for pinion and gear, that is 230, and Lewis form factor for pinion and gear is calculated, and calculate the product of these two. The value whose sigma naught y is less, that is the weaker. Or if the material for the pinion and gear are the same, then pinion is the weaker member. Step 2. Design. Step with tangential tooth load. The tangential tooth load equation is given here. Here, in this problem, the condition is not given. Then assume medium shock and 8 to 10 hours duty per day. For that, the service factor is 1.5. Refer the table 23.13. For weaker member, calculate R1. That R1 is in terms of moduli, and N1 is the speed of the weaker member, that is 1200 RPM. Substitute all the values in the equation 23.87b. We get the tangential tooth load equation in terms of moduli, that is the equation number 1. Step B. Tangential tooth load from the Lewis equation. The equation is given here. For weaker member, the allowed statistics value is given, and select face width is, that is a 10 moduli. Usually you select that is the 10 moduli. Already calculate the Lewis form factor for the weaker member. P is the circular pitch, that is equal to pi m. Put all these values in the equation 23.93 we get. We get FT equation, tangential tooth load equation, in terms of moduli and velocity factor. That is the equation number 2. Now equate the equation number 1 and 2. We get the equation number 3. Then calculate pitch line velocity of the weaker member. That pitch line velocity is in terms of moduli. By trial and error method, find the moduli m. Select standard moduli m from the table 23.3. Trial 1. First we select standard moduli 3 mm. Then calculate pitch line velocity. If velocity is less than 7.5, we use this equation. Then calculate the velocity factor. Put all these values in the equation number 3 we get. If LHS value is less than RHS value, then the moduli selected is not suitable. Then go for the trial 2. Then the same procedure is followed as the trial 1. Select moduli equal to 4 mm. Again calculate the pitch line velocity. If this velocity is less than 7.5 meter per second, then again we use the same equation. Calculate velocity factor. Put all these values again in the equation number 3 we get. Now LHS value is greater than the RHS value, hence the selected moduli is suitable. Then finally we get moduli equal to 4 mm. Then tangential tooth load is this value, and also calculate the face width. 10 mm is nothing but that is the 40 mm. Next, check for the stress. First we calculate the allowable stress, then we calculate the induced stress. If induced stress is less than the allowable stress, then the design is safe. Step 3, checking. Step A, dynamic load. The dynamic tooth load equation is given here. In this equation, all the parameters is known except the value of C. Refer the figure 23.34a. For carefully cut teeth or close to gate and model equal to 4 mm, the error we calculated is 0.025 mm. Next, to find out the value of C, refer the table 23.32. The combination of the pinion and gear is steel and steel, and for alpha equal to 20 degree FDI and error 0.025 mm, we get the value of C is 290 kilonewton per meter. Convert in terms of Newton per mm. Then substitute all these values in the equation 23.155. Then we get the dynamic tooth load value. B bit wear load Fw. The wear load equation is given here, where D1 is the pitch circle diameter of the pinion. Already we calculate the mode length, then calculate pitch circle diameter. Already we calculate the face width, then calculate ratio factor. Now apply the condition. For safer design, the wear load is greater than or equal to dynamic load. Substitute all the values, then we get the K value is greater than or equal to 1.701 MPa. We said that is the equation number 4, where K is the K equation is given here, where E0 is the equivalent Young's modulus. The E1 is the Young's modulus for the pinion, E2 is the Young's modulus of the gear. Then calculate equivalent Young's modulus. The equation 4 becomes, then calculate sigma FAC value. Then refer the table 23.37b. For alpha equal to 20 degree FDI, K value is greater than or equal to 1.701 MPa. Sigma FAC is greater than or equal to 854.6 MPa. Surface hardness for pinion is 400 BHN and surface hardness for gear is 300 BHN. This is the table of 23.37.